In our last video, we learned how gradient boosting is a team of experts working in sequence. In this video, we'll go over the details of how these experts build their individual trees. By the end of this video, you'll have an intuitive sense of how XGBoost builds its trees by scoring the leftover mistakes and selecting the single best split to fix those errors. Welcome to Scovia Labs, where we make AI concepts feel like everyday ideas. Let's look at a simple example where the training data consists of power consumed and temperature. The goal is to predict the power consumed based on temperature. Note that the algorithm will look like an overkill for this small example. The idea is to show how it works on a small dataset, which helps imagine how it might work on a bigger one. Let's start with gradient boosting. Consider an example where you're predicting the energy demand of a building based on the temperature outside. And a plot of it looks this way. X-axis is temperature and y-axis is power consumed. Given this data, goal is to build gradient boosting tree. First step in gradient boosting is to calculate the mean of the prediction variable, which is the power consumed in this case. So the mean value is equal to 8.8 here. After this, we calculate something called the residuals. Residuals are the errors in prediction compared to the mean in this case. We calculate another metric called the Similarity Score, which is sum of all residuals, which are then squared and divided by the number of samples. Note that the positive and negative residuals cancel each other out, since we do not square the residuals before adding them. Having a large value of similarity indicates that most errors are in the same direction and is considered good. The next step is to build the tree. This is a special tree, which is built quite differently compared to a vanilla decision tree. We'll show three candidates, 2.5, 7.5, and 12.5. The recipe is the same each time. So let's start with the threshold 2.5. First, the residuals are sent left or right based on whether they satisfy the condition of x being less than equal to 2.5. Then we compute the leaf value in each child, which is the mean residual in that child. This turns out to be 5.2 for the left child and negative 0.5778 for the right child. After this, we compute each child's sum of squared errors and similarity. Finally, we compute the gain, which is the sum of squared errors of the root node minus 30.04 as well. When we execute this step with different thresholds, we get different gain values in each case. Among these, 7.5 gives the largest gain, so it becomes our root split. We can grow this tree one more level. We can split either of the child nodes. We'll choose the single split that gives the biggest additional gain. Splitting the left child results in two singletons giving a gain value of 4.5, while splitting the right child at a threshold of 37.5 provides a gain of 35.0417. Since 35.04 is greater than 4.5, we split the right child at 37.5. So that is how XGBoost builds its trees, by calculating the error, scoring the similarity of those errors, and selecting the split that maximizes the gain. Now we have seen that this tree generates large, strong correction values. But in the real world, we never add those corrections at full strength. The extreme part of XGBoost is all about control. In this model, that control comes from three crucial concepts that we use to manage the final result. Learning rate, which is our volume knob that ensures that each tree only whispers a correction rather than full volume. Tree capacity and stopping, which is essentially rules that we set to keep each tree simple and honest. The third one is regularization, which is our skepticism knob that prevents the model from trusting fragile, noisy data. We'll cover those crucial concepts, the learning rate, the tree capacity, and the regularization in the next video of this series. Thanks for joining us on Scovia Labs. Hit that subscribe button for more insights, and as always, stay curious.